On Christmas morning, 2021, a virtual miracle happened. A $10 billion telescope rose from the Earth in an Ariane 5 rocket from Fritz-Guianen. The spin of Earth makes equatorial regions especially beneficial for the launch, as it can give the launch vehicle an extra push. Earlier in the year, we had the pleasure here at Ingram Planetarium of sitting down with scientist Dr. Hassan, who has been on the James Webb Project for nearly 30 years. In this interview, she discussed exactly how the telescope works and what we hope to learn with it. Now, Dr. Hassan, she is a NASA program scientist for NuSTAR, the Keck Observatory in ADCAR, and is a deputy program scientist for the James Webb Space Telescope. In her role as a program scientist, she makes sure that each project's mission remains possible and true to NASA's strategic objectives. Dr. Hassan has been a program scientist for many other NASA missions as well. You can learn more about her in a link I'm going to post down below.
The design, building, and testing of the Space Telescope turned out to be much costlier and more challenging than it was originally conceived. But we've overcome all those challenges.
Now, many of us have a very specific image in our head of what a telescope looks like, but the James Webb Telescope looks very, very different. Can you talk a little bit about some of its components and why its presentation is so divergent from our normal idea of a telescope?
So James Webb is, the design of it is what is called a 3-mirror astigmat. In other words, it consists of 3 curved mirrors designed so the optical errors are minimized. The primary mirror is about 6.5 meters in diameter, which is around 21 feet. And it will, in order to fit it in the rocket, it has been designed in 18 hexagonal segments that can fold up like an origami. And the light from objects being observed first hit the primary mirror, and then it is redirected to a smaller secondary mirror, which is mounted on 3 struts which extend out in front of the primary mirror. And the light then goes through a hole in the secondary mirror to the back onto a tertiary mirror, from where it's directed by steering mirrors into the science instruments, which are at the back of the telescope mirror. And to protect the telescope from the heat of the radiation of the sun, there is a 5-layer sun shield about the size of a tennis court that unfolds under the telescope. Now, since the telescope will be orbiting in space at a stable point, which we call L2, and it is about 1 million miles, which is about 1.5 million kilometers from the Earth, and it is in the exact opposite direction from the sun. So the sun shield is sufficient to protect the telescope from the sun, and it does not need to be enclosed in a tube like Hubble. So in a nutshell, that's what Webb looks like and how it will operate.
That's awesome. And I love doing origami, so the fact we use origami for a spaceship, I think, is really cool.
Yes.
Now, how long have you worked on the project? I mean, this has been going on for quite a long time, as we discussed. So how long have you been with the James Webb Telescope Project? And can you tell us a little bit about your experiences on it?
Yeah, so I actually have worked on this way back when I was a scientist at Space Telescope Science Institute in Baltimore. I actually participated in the 1989 workshop where scientists discussed the Next Generation Space Telescope, or NGST, which would be the successor to Hubble. I continued work on NGST. Later, it was named the JWST, or the James Webb Space Telescope, after joining NASA headquarters in 1994. And I have been the NGST and later JWST program scientist, and I'm now the JWST deputy program scientist. Now, the role of a program scientist is that we are responsible for working with the science community to set the science requirements for the mission and the science instruments. Now, during the development phase of the mission, our duty is to ensure that the science requirements are being met. And finally, the program scientist is responsible for the science program that will be executed by the observatory. So following are some examples of my experiences on the project. During the early formulation phase of the mission, I led the solicitation for proposals for early technology development, had them reviewed and recommended for selection. I set up an interim science working group, prepared its charter, and conducted lengthy discussions before we came to a consensus on the science requirements. A decision on the science requirements on the science instruments was also a challenging one, both on the nature of the instruments and on the partnership between the three international agencies. I participated in intense negotiations on the mid-infrared instrument, which was added as a partnership between NASA and ESA. So we were going to share one instrument, whereas the other instruments belonged to individual agencies. On that fateful day, September 11, 2001, I was conducting a review in Washington, D.C. for NASA to decide which of its centers would manage its contribution for the mid-infrared instrument. So that really stands out in my mind.
Yeah, definitely. It's so incredible that all of that was going on all at the same time.
Exactly. I mean, it's that moment just ingrained in my mind. And so whenever I think of the mid-infrared instrument, my mind goes back to that day. Well, so coming to the brighter side, in preparation for conducting science with the observatory, I have contributed to numerous activities, including the selection of the early release observations. I have supported the program scientists for setting policies for selecting science observing proposals for JWST, and in outreach to the scientific community and the public. So I think that is one of the most exciting things right now, to talk to everyone, to this audience and anyone else, and tell them about the wonderful, wonderful telescope that we are all about to launch, and just sitting at the edges of our chairs waiting for the launch.
Now, the James Webb Space Telescope is being hailed by many in the public as the next Hubble, and this is especially amplified by the fact that the Hubble is aging. It's been experiencing some problems related to its age, but they're very different in a lot of ways. So can you speak a little bit about how they're similar, but also very different in how they operate?
I would say that perhaps JWST is most similar to Hubble in that, like Hubble, it is expected to go where no telescope has gone before. Just as Hubble made discoveries of phenomena such as dark energy, atmospheres of exoplanets, finding black holes at the centers of galaxies, and many, many more, which we didn't even know existed at the time Hubble was launched. We expect JWST, in addition to studying what it has been designed for, to show us wonders of the universe that we are yet unaware of. There are many differences between the two observatories. Following are just some examples. JWST has a 6.5 meter diameter primary mirror compared to Hubble's 2.4 meters, or about 8 feet, mirror, making it 100 times more powerful. Whereas Hubble observes primarily in the ultraviolet and visible with limited infrared capability, JWST is an infrared observatory, which will be able to see far back in time and more distant objects than Hubble can see. For example, Hubble can see the equivalent of toddler galaxies, while Webb will be able to see baby galaxies. Hubble orbits the Earth at an altitude of 360 miles, which we call a low Earth orbit, making it serviceable, while JWST will be about 1,000,000 miles from the Earth and orbit the Sun, which will keep it cool as required for an infrared observatory, but it will not be serviceable. The telescope design for Hubble is a traditional Cassegrain with two circular mirrors made of glass. They're just all one piece, and it is coated to optimize for observations in the ultraviolet and visible. And the whole structure is enclosed in a tube. Whereas Webb, the primary mirror is made of beryllium, which is very lightweight, and it is coated to optimize for observations in the infrared. In fact, it has a thin gold coating. And it consists of 18 hexagonal elements which fold back for the launch of the telescope. The JWST science instruments have far more capabilities than Hubble. For example, they will be able to view larger patches of the sky and get spectra of several galaxies at the same time. They will be able to study the atmospheres of exoplanets, taking us beyond the discoveries of Hubble.
That is so cool. I can't wait to get that the first bits of data when it's released. Now, speaking of what to expect as the data comes in, many space missions do have specific goals, and anything beyond that's considered kind of a welcome bonus. I know the New Horizons mission was like that. Are there any specific goals for the JWST, or is it more of a shared tool that many different research groups are utilizing for different goals?
The JWST is certainly a very powerful telescope, and as I've said, that we hope to make discoveries we haven't thought of before. However, the primary aim of JWST is to shed light on our cosmic origins. It will observe the universe's first galaxies, reveal the birth of stars and planets, and look for planets with the potential for life. So these are some of the primary goals for what JWST has been designed for. So currently, competitively selected early science observations will be conducted during the first 5 months of the science operations, and the data will be released immediately to the public. Scientists from 44 countries applied for observing time for the first cycle of science observations. The science proposed spans all the JWST science goals, and the early observations will demonstrate the capabilities of JWST and give us a flavor of the science that is to follow.
Now, after that initial 5 months, since it is more of a shared tool that the world utilizes, how do other researchers kind of apply for time to use it for observing? Is there a process for that?
Yes. The Space Telescope Science Institute in Baltimore has been contracted by NASA to execute the science program for JWST, just as it is executing the science for Hubble. STSCI, or Space Telescope Science Institute, they have an open solicitation for proposals from scientists around the world to conduct observations with JWST. The proposals are evaluated by peer review committees, which are set up by the Institute, and the selections are made by the STSCI director. And the data, after the observations are made, the data is placed in a public archive at Space Telescope Science Institute. And this is the Mikulski Archive for Space Telescopes, or MAST for short. And it is available to the public. All the data is available to the public after a 1-year period of exclusive use by the proposing team. And exceptions are that data which is obtained during the director's discretionary time will be made public immediately, like the early release science observations I mentioned earlier. And sometimes scientists voluntarily make their data public before the period of exclusive use is over. So all the data that comes out of the telescope is available to the entire world to use. And we certainly expect scientists around the world to use that data and produce the best science for us, in addition to those whose proposals are selected for specific observations.
I think that really speaks to just how widespread NASA's resources are. A lot of times the public doesn't realize just how much all of this data from all the telescopes that we have really contributes to a wider group of missions, which kind of brings me to my next question. When we look back on missions in the past, the Apollo missions for one very prominent example, we have a lot of technologies in our everyday use now because of space exploration. So in the length of time that we've been working on this project, are there any technologies that we have in today's world as a result of the work on the James Webb Space Telescope?
Indeed. In order to meet the James Webb Telescope's science objectives, numerous new technologies had to be invented. Lightweight mirrors, lightweight structures, software, and a whole plethora of technologies. So let me give you some examples of those that have benefited other advancements. And so I'll give you four or five examples. So one is the wavefront sensing technology, which was developed to accurately measure the shape of James Webb Telescope's mirrors. And this has led eye doctors to now use the sensor for fast eye mapping, diagnosis of ocular diseases, and potentially to improve surgery features. So what an amazing application that is to humankind. Then the high-speed test devices were developed that used pulsed lasers to freeze out vibration effects for nanometer precisions. The technology now generates millions worth of revenue from aerospace, astronomy, semiconductor, and medical industries. So it has a really wide application. JWST's investments in cryogenic application-specific integrated circuits, or ASICs, has made these specialized small circuits programmable. And one of the applications is that it is now flying on Hubble, where they were used to repair its advanced camera for surveys during the last servicing mission. And another example are the advanced infrared detectors, which were developed for JWST's instruments. These are now the universal choice for astronomical observations in space and on ground technology. And this technology is also being used in earth science and national security systems. And I'm sure there are many, many more, but these are just a few examples of how the technology development for James Webb has benefited our society.
That's awesome. Well, that kind of concludes my questions for you, Dr. Hassan, but do you have any final thoughts that you'd like to leave with our visitors today?
Well, I would say that the James Webb Telescope is really a testimony to the imagination, how far the human mind can go, and what we can do and what we will learn from it. And it will inspire generations of students and the public, and for doing great things in the future. and, maybe even determine what our destiny will be.
Maybe so. As Dr. Hassan mentioned, launch was only the first critical milestone, leaving the scientific community and the world at large in suspense. It took nearly a month to know if this global investment would be a true success. Because of its enormous size, the JWST had to be folded like origami to fit into its launch vehicle. It would need to unfold remotely into its final form at distances well beyond human reach. The first thing to bloom was its sun shield, which would keep the scope's temperature regulated. On December 28th, 3 days after its launch, we received confirmation of deployment. Its second milestone would be the deployment of its primary mirror segments. Over 2 days, scientists on Earth remotely positioned the two sides. After all major structural maneuvers were complete, and it reached its final destination at L2, 1 million miles away from Earth, it would then undergo the month-long process of preparation for scientific operations. In March of this year, the JWST team confirmed optics were working as expected. This keeps us on track for a summer release of its very first image.
Ingram Planetarium has been selected as a Webb Space Telescope community event host. We are excited to share some of the first photos taken by the James Webb Telescope. Keep an eye out for announcements regarding our special event in July.